Electrification is a very important thing which required by all the people who are present. Everyone requires electricity. But the problem is that the location. A person whoever is located nearby to the power source, the power availability challenges will be reduced in comparison to a person who is living far away regions. So we have to keep in mind the locality of the place where a person is situated. So keeping in view, there may be challenges that electrification is a basic need of all the individuals. And the person who is located in hilly areas or in islands, the availability of electricity becomes a very important challenge because the grid connectivity is provided by the conventional energy systems, and the conventional grid is becomes a very expensive thing whenever we are connecting these places, as well as the population is very limited. And due to the population limitation, if we provide electricity through grid connectivity, the required amount cannot be extracted. Means payback period will be very large. So this is a very important challenge that we have to look around to provide electricity. Now, what is the remedy? Remedy is that if we provide off-grid electrification, if we provide off-grid electrification, and if we are able to ensure that we can provide the electricity with, and we can provide the continuity of power, that will be a very important thing. And the second challenge is that cost of the overall system and its feasibility. Even if we are able to design an off-grid system, then also there can be a possibility that how the overall system can be operated, because we have to ensure that the people who are living there, they must have the proper training to operate the system. Because the other people who are living in cities, very difficult to reach in these rural areas in a quick amount of time. Again, another important, so this problem as well as the problem of establishing an off-grid system, we have to keep in mind what are the constraints that we have to consider for designing the system. The constraints can be economic, technical, socio-political, and environmental. So basically the constraints are divided into these four categories. Economic means cost of energy, or we can say the overall system cost, implementation, maintenance, and replacement cost over the lifetime of the system. That comes into the economics part of the constraint. Then the technical part, which is basically comprises of power system reliability, power supply reliability, then technical problems such as the conductors and the availability of power, the quality of power. If we talk about the socio-political challenges, the socio-political is basically the social acceptance of the thing. If we are not able to advertise or market properly that an off-grid system will help to eradicate various problems of these villages, they will not install these systems. So we have to make sure that they know about the proper awareness may be there. As well as if we provide some job creation, means some training, if they have proper training to operate the system, so we can provide the job creation scenario, they can maintain the overall system. And finally, the environmental part. Because in the present scenario, there are different systems. Diesel generating system is there. Okay, we are balancing, we are maintaining a hybrid system comprising of non-renewable generating systems as well as renewable generating systems. So sometimes we can use diesel generator or some oil-based systems. So there, as well as in biomass also, the emission part is very important. CO2 emissions and greenhouse gas emissions will be there. So we have also we can consider these important phenomena, and we can consider it into the environmental part, environmental constraint. Now, selection of these parameters, different group of parameters for designing the system is very vital. So you have to keep in mind what are the important criteria and constraints which you have to prioritize. So you have to pick 5 to 10 important constraints to design the problem, whichever is of higher priority. Then another important challenge is longevity of the components of the system and their regular maintenance. So that I told you that there can be faults in the system. So how to eradicate that fault in a very rapidly. Similarly, regular maintenance we have to perform, and we have also to. There can be a possibility of some damages, so we have to replace them. Finally, the power loss in the off-grid system. If off-grid system is there, we have different generating systems, we have the load centers, but we have to think about the power lines. So after designing the system, we have to think about what type of conductors that you have to select so that the power can be delivered from the generating systems to the load centers. So we have to apply the power loss, that is load flow analysis we have to operate so as to select the conductors. Now, keeping in mind the challenges and remedies, I have considered a case study. Okay, so there is a case study, you can say that off-grid electrification of a hilly rural area. So hilly rural area is a challenge. So that's why I had considered this in my work. So there we have to select some cluster of villages. There can be 5-7 villages which was previously unelectrified, but now they have a smaller amount of electricity is being available there. But a cluster of villages are a set of villages that are 5, 7, or 10 villages, or a group of villages. Now, after selecting this group of villages in hilly area, we have to think about the load estimation. Because without demand, we cannot go for resource estimation. Firstly, we have to pinpoint, we have to determine that what is the demand. So demand can be electrical demand, it can be thermal demand. So different demands we have to think about. So in that terms, what are the components which are consuming the energy in these villages? So in terms of that, then we have to think about how, in what hours these components are being operated. Some types you can think that in summers we require fan around 20 hours. Okay, so we have to think that 20 hours can begin from 6 a.m. to 2 a.m. It can work for 20 hours. It can be operated for 15 hours. That we have to think about because electricity is not there. So then we have to distribute. In this way, we can distribute the demand in 24 hours. After achieving this 24-hour demand variation, we can think about the resource estimation. Because we have finalized the demand assessment, we can go for the resource estimation. So in resource estimation, we have to think about is solar radiation available? So what is the amount of solar radiation which is available there? Then in case of hydro, we have to think that what is the head and discharge which is available there. Biomass, in case of biomass, we have to think about what is the village area. We have to demarcate the village area. In the village area, what is the amount of forested area and what is the amount of agricultural area. So on the basis of that, we have to think what type of plantation is there. So according to that, what is the amount of forest foliage or crop residue we can collect. Similarly, what is the cattle dung in terms of the animals which are there. So these are the basic different type of resources which are available. You can also think of the wind potential. So because it was not there, I had not considered. So because our demand is projected in terms of kilowatt, because our demand is in kilowatt, so our generation needs to also be converted into kilowatt. So there are some modelings, you can see modelings of the system components, which are solar PV, hydro. These all powers are regulated in terms of converted into power in kilowatts. Then finally, with the help of this mathematical modeling, you will find the resource assessment is done. After resource assessment, we have to put it into the mathematical equation to find out the power equation. Now we have to match this power equation, that is generation, with the demand all the time. Generation cannot be less than the demand. Otherwise, there can be a failure or shortage. So we have to keep in mind the overall generation needs to be greater than the overall demand. So this is the power equation, power balance equation. This will be operated for a year. In my simulation, I had used this comparison, that is power generation versus power demand. We have equated this for an year. Okay. there are different objectives and constraints. What are objectives and constraints that I will discuss? But actually the constraints and objectives are the part of those four important factors that I have discussed. Now, after these conditions, we can go for the sizing of the system. Now, in case of sizing, you can say the hydro potential, that is head and discharge, is finalized. You cannot change it. So hydropower potential, that is 10 kilowatt or 15 kilowatt system of hydro is there. So we can implement that system. We cannot change the size of the hydropower. Similarly, the size of the biomass we cannot change because it depends on the crop availability and forest availability, forest residue availability of a village. So it is also fixed. But the variation, where there is a variation, solar radiation. Solar radiation is available, but we can increase the number of solar panels depending on our requirement. Similarly, the number of batteries we can increase. Similarly, we can increase the number of diesel generator. I have considered diesel generator as a backup system whenever there is a shortage of resources. These resources, along with that, battery SOC, state of charge, has been reached. That I will discuss. So I had also considered diesel for charging the battery. It is the last resort. Whenever the renewable energy systems and the batteries are unable to supply the demand, in that case, we can use the diesel generator for either charging the system, charging the batteries, as well as supplying the net demand. So this is a part of dispatch strategy, that is how the power can be supplied from these generator or sources to the load in a particular way. Now this we can say that demand equal to generation. It is shown in the you can say below. Okay. So this is the important equation that we have to fit. If this is met, if this is not met, we have to increase the size of SPV or batteries or diesel generator in our algorithm. Okay. Finally, the cost of energy can be established. Now for this, as I had gone through the methodology, this was the methodology, overall methodology. In this case, you will find that there is Uttarakhand state, and there Almora is there, Almora district is there, and in Almora district there is a Dholadevi block which is demarcated, and finally this Dholadevi block is expanded and magnified, and you can say that there are 7 villages. 5 villages are considered to be a first cluster, and 2 villages are considered to be the second cluster. Okay. Now we can, according to the 2011 census, the overall population is given as 2,500, and the number of households I have calculated because it is very difficult to establish what is the total number of households. Now, basically, you can think of that 4 to 5 members are there in a particular family. So that's why I have considered divided it with 5 or divided it with 4, whatever thing that you want, or divided with 6 also you can perform. Then you can find out the total number of households there. Clearly, what is the location, latitude, longitude, and the elevation? Now, similarly, we can see that the demand, how it can be regulated, it can be constructed. Demand curve. Firstly, we have to think about what are the domestic, commercial, and industrial loads. Industry, we will take one at a time. Domestic loads. Domestic loads, we can say lights, television, fan, radio, etc. are there. Ratings are given, and total numbers are given according to the requirement. Since we have considered 559 total number of households, so 1,118 is the multiplied by 2, 559 into 2. Okay, so we have considered that a house will be there. You can design your house accordingly. You can think of it in your mind properly. That if 2 rooms are there, so we require 2 lights. So that will be 1,118. Okay, similarly, television can be there in some houses, it cannot be there. Fans can be there, radios can be there. Similarly, what is the total number of hours for which they can be utilized in a day? 6 hours, 2 hours, like that. So what is the overall load that you can find out, summer and winter? Now in commercial loads, you will find some shops are there in villages. There can be flour mill, okay? As well as even industrial loads, because this is a hilly area. So wood is there. Wood cutting machine will be there. That is sawmill, which will regulate the amount of total selected logs. Okay. 5 kilowatt system will be considered there. Total number of hours of operation and kilowatt is given. Now, similarly, societal load, some post offices, gram panchayat rooms, hospitals will be there. Similarly, you can find out the load. Okay, some street lights will be there because you have to think about in future terms. There can be a possibility of street lights. Then water pumping system will be there. Now, accordingly, you can find out the total domestic, commercial, industrial, and societal loads in annually. You can project it. Okay. Finally, you can understand and you can formulate this demand curve. This is the demand curve. You will find that for summer day, for winter day, this is according to the data which is provided. Okay. Now you can think of the now as we have completed the demand estimation, we have obtained the demand curve that is finalized. Now we can move for the resources. In the resource assessment, we can think of the micro hydro potential which was there. So discharge versus time. Basically, time is of our simulation is being operated for 1 year. So 365 into 24, that is 8760 number of hours. If our time is 1, time is considered to be unity, so we can find out the discharge. Okay. What is the total amount of discharge which is available for a particular time period? So available discharge is reducing. It is maximum. Okay, it is reducing to 0.0845. You can see at the last 0.0845 is the minimum discharge which is available all the time. So there is a benchmark that is 85% of the discharge time. Of the overall time, what is the available discharge for the 85% of the time? That you have to consider for the overall system designing. Okay, for 85% of the time, 0.085 meter cube per second discharge is available. Height is 23 meter and efficiency is 0.8 and 15 kilowatts. So you can directly use this formula GQ, rho Q, GH into efficiency. You will find that the power of the hydropower. Okay, hydropower divided by 1000 to convert it into kilowatt. That is 15 kilowatt. Similarly, the hydropower cost. In terms of costing, we will find that rated capacity is 15 kilowatt, rate discharge is there. Okay, head is given, then efficiency is given. Civil works, there will be some amount of civil works for construction of the hydro turbine system, overall system. Pen stocks for moving the water from the upper reservoir to the downstairs where the turbine is being placed. There will be some pen stock. Cost of the turbines, there will be bulbs. Okay, cost of the generator and control equipment, lifetime of the image. So these factors you have to consider whenever you are designing the image. Micro hydropower. Micro hydropower means less than 15 kilowatt system. We have up to 15 kilowatt system. Now again, if we think about the biogas potential, how to regulate this in terms of power that I'm talking about. That in case of biogas, we have to think about what is the total number of animals in these villages. Cows, buffaloes, goats, horse, mules, what are the total numbers? In these 7 villages, the total numbers are given. Okay, 4123 is the total number of cattle population. Now we can think about the total cattle population, dung availability. For each type of cattle, the dung availability for a day will be different. If we multiply it with the dung availability, we will find that total dung available. Then if we multiply it with efficiency 75%, then we can convert this and we can multiply with 0.038 in case of cows. That is biogas yield in meter cube. Okay. So biogas yield is given in meter cube. So 1 kg of dung will be converted into 0.038 meter cube of the available biogas. It can be converted into biogas. So overall total dung, if we multiply it with 0.038, we will obtain the total biogas yield in meter cube per day. This kg is converted into meter cube. 1 kg is equal to 0.038 meter cube. Okay. In this way, we can convert it into meter cube per day. So for each village, we can regulate, we can find out the total biogas available in daily basis or yearly basis. We can regulate it. Now, this is an important phenomenon that cooking demand. Instead of providing cylinders if we are able to supply the biogas, convert it into cooking demand. So the total number of population, and we know that each in a household, what is the total number of total amount of biogas which is required. So you can find it was estimated that 600.48 meter cube per day was the total requirement. Okay. So 849.3 meter cube per day is the total available biogas which is collected, of which 600.48 meter cube per day is used for cooking. So remaining can be used for power generation. So 248.82 meter cube per day is used for power generation. Now, according to that, what is the biogas system which we can implement? Two systems of 10 kilowatt can be installed in a particular two villages, and one is of 5 kilowatt system which can be placed in a particular village. Now we can see in similar way what is the civil work cost, because in the biogas system also you have to construct the gas holder type system, or that system you have studied. So KBIC plants. So for that you have to give some certain amount of money, that is 3 lakh rupees. Some these data I have collected from MNRE website, Ministry of New and Renewable. Okay, that is what is the for a particular kilowatt, what is the available civil works cost, and different costs will be there. Engine generator cost will be there, efficiency will be there. Okay, and what is the total number of hours, because it is a diesel generating system. Because instead of diesel, we are using the biogas, and biogas is a form of gaseous form. It is rotating the generator. Actually, it is you are getting the output. Now, total number of hours of operation is 16,000. Okay. Similarly, for the 5 kilowatt system. Now, mathematical model. This is important because now you are converting the available biogas into electricity, into power. So in this case, the power equation is PV is given as TG into CV VM into efficiency of biogas generator divided by 860 into T. Basically, the value TG is the value which is obtained there. What is the value? 248.82 meter cube per day is the value which is available per day. Okay. So that is TG, meter cube per day, into CV. CV means calorific value of the biomass. Calorific value of the biomass is given in kilocalorie per meter cube. Kilocalorie per meter cube. So we can say it is kilocalorie per day. Okay. Into efficiency of BGG divided by 860. So we know that kilocalorie by 860 is in kilowatt. Okay. So 860 we are dividing to convert it into kilowatt. And divided by T. T is the total number of hours of operation. We are operating it for 9 hours. Okay. We are operating it for 9 hours. We have estimated this thing. So accordingly, after dividing it with 9, we are finding that around 25 kilowatt of the system we can implement there. And we have divided according to the resource availability. We are dividing what is the system we can implement at a particular village. Now, similarly, biomass forest potential. In case of forest potential, we have to think what is the villages, name of villages, total area, forest area. And in forest area, we have to think about, because leaves will fall and barks will fall. So there can be chances that you can collect these in hilly areas and you can convert it into smaller parts. You can convert it into brackets. You have heard about this term, brackets? So brackets is a term which is a cube-like structure. You can convert the biomass into cubical shape and you can feed it into biomass gasifier. So how you can convert it? By getting the amount of total forest foliage, you have to cut it down, then you have to compress it to convert it into brackets. Okay, brackets are of cube shapes. Okay, then you have to dump it in the biomass gasifier. So 160 kg per hectare per year is the overall available. 160 can be multiplied with the overall hectares for different topography. You can find out in hilly areas, the distance between the trees is very important. A tree is located here, another tree is located 5 meters nearby. So you can find out in normal way, whenever human beings are not involved, we will find that the trees spacing will be limited, constraints will be there. So different types of vegetation will have different spacing of the trees. Okay, so the available foliage will be different in that case. So here in this way we can calculate the 60% of the foliage you can collect. You cannot collect 100%. Sometimes you can also limit it for 40%. Now similarly the crop potential, the area is given. What is the crop area? In Rabi, in Kharif season, what are the different type of crops which are being generated, which are being grown? Okay, what is the amount of area? That is 48% is of wheat. So we can multiply 48, that is 0.48 into 10.13. We can get the overall area wherever wheat is being grown. Then we have to sum it up. Okay, total amount of wheat which can be collected. Then grain, productivity of grain and grain productivity, everything you can calculate it, and you can find that what is the overall biomass which can be collected. It is of 91 tons and 35 tons of the forest foliage which can be collected here. Now important point is to be considered here. If we sum up this 91 with 35, we can arrive with a 127 tons value. 127,000 kg per year can be directly written as 127 tons. Okay, 127 tons of biomass is available. Now similarly you can think of the overall system cost, okay, of 15 kilowatt system. Basically in case of power, we can think of the same similar kind of equation, that is TB into CBVM. TB is the total available biomass. That is, what is the value there? 127 tons. So 127 tons into CBVM. What is calorific value of the biomass? So whenever you are multiplying the calorific value, that is kilocalorie per kg or kilocalorie per ton of the biomass which is available, then you can directly cancel out the units, that is tons per year. TB is in tons per year and CBBM is in kilocalorie per tons or kilocalorie per kg. So kg will be cancelled out. You will find that it is kilocalorie per year. So since it is in year and we have to operate it in hourly basis, we have to divide it with 365 days. We have to convert it into hourly basis and daily basis. So we are dividing it with 365. Then 860 into T. 1000 is multiplied because we are converting into kg. It is in tons. We are multiplying with 1000, that is in kgs, because CBBM is in kilocalorie per kg. That's why. Into efficiency of biomass. Now here you can find out that around 30 kilowatt of the system can be implemented. So there are two systems of 15 kilowatt which can be installed in two villages, which are now government saving. Now, important point to consider here, we have seen the demand curve. This is the demand curve, and we can see that from the 10th hour, the demand is maximum around 9 to 10 p.m. The demand is changing, but actually the demand is in this period, the demand is maximum. And we can operate the biogas generators in a particular way. It is in your control how to operate them. That's why the biogas generators are being operated in this period only to reduce the amount of peak demand. Okay. That's why you can see that from 10th hour to 22nd hour, the biogas generators are operated in this way. So biogas generators are biomass gasifier and biogas generating system, both combined. Now, if we talk about the solar energy potential, you can see that there are, for different months, the radiation is changing. The radiation is changing. Similarly, the temperature is also changing, because temperature plays a very important role in getting the overall power output in solar PV. So you will find that the overall main equation is PSPV equal to number of modules. Overall power output of the solar module is given as number of modules into VOC open circuit voltage into short circuit current into fill factor, divide by 1000. So in this way you can find out the PSPV. Now if we talk about the specification of SPV, we have considered two different types of SPV system for optimization basis. So here the overall open circuit voltage, everything specifications are given here. Now similarly for diesel generator, there are three different types of diesel generators. Ratings of diesel generators was considered 10, 20 and 30 kilowatt of these costs. Okay. Now important point to consider is that CO2 emission from diesel generator. Initially I had considered the diesel cost to be 52.13 rupees per liter. It has increased so much. Okay. But CO2 emission from diesel generator is very important. Kg per kilowatt hour. So 1 kilowatt hour of operating a diesel generator will emit around 0.772 kg of CO2. That is very much, huge amount. Okay. So by getting this important information, we will implement this as an important constraint. So we will look into it. Then the number of operating hours, 16,000 hours only we can operate the diesel generator. Then we have to replace it. Now this is the overall scenario of the assessment. MHP 360, that is 15 kilowatt system. For a day, 15 into 24 is 360. Okay. Biogas potential, biomass potential and solar energy, these things we can directly find out. Now we can look into this configuration. Configuration is that we have think about the load. We have load is finalized. Okay. We have talked about the diesel generating system. DC renewable generator is basically the solar generator, which is being stepped up with the help of boost converter and is fed into the DC bus. Similarly, the battery bank is there. There is a charge controller and there is a dump load. And charge with the help of charge controller, you are connecting it with the DC bus. Now there is a bidirectional converter. It is linking the DC bus with the AC bus. And finally, there is a AC renewable generators. What are AC renewable generators? These are basically MHP, hydropower, and the biogas systems. Okay, these are the AC renewables. Now this is the overall configuration of the hybrid energy system. Why it is known as hybrid? Because there is a presence of diesel generator. That's why it is hybrid. Otherwise, it will be known as integrated renewable energy system. Now, if we think about the battery modeling, here the battery EBAT minimum is given as depth of discharge of battery into EBAT nominal. Number of batteries can directly be calculated as the dependent on the V bus voltage. What is the DC bus voltage you are considering? In DC bus voltage, you are considering 48 volt. If you are considering 48 volt, you have to think about the battery bank, total number of batteries to be connected in series. You have to make up a voltage of 48 volts. Otherwise, it cannot be compatible. So what are the total number of batteries which can be connected in series? You can directly find out by thinking about the bus voltage, DC bus voltage. Similarly, the remaining number of batteries can be connected in parallel. Okay, for increasing the ampere hour. Now, during discharge and during charging, what is happening? During discharging, you have to think about what is the EAC. EAC is the sum of all the energy provided by the AC generators. That is MHP, BGG, BMG, and diesel generators. All these generators are the AC generators. For a particular time, T is given for that particular time. DC is given as ESPV plus EBAT into efficiency of charge control. Now, EBAT for a particular instant, you have to think about what is the previous energy state of that battery. We have to perform the charging or discharging. We have to think about the what was the previous value of the EBAT. That is EBAT T minus 1 minus efficiency B is given. That is the round trip efficiency of the battery. Sometimes theta B is considered to be the charging efficiency. Sometimes it is considered to be a discharging efficiency. Both can be different. Now there is a difference between it is being written up, but actually what is there? It is the difference between the demand minus generation. That is to be used for charging the battery. Okay, EBAT T minus 1 minus this value will be given as what is the amount of energy which is the remaining part. It can be used to charge the battery in the PA tower. Now, this is very interesting point that I will cover. Okay, replacement cost of the battery bank and its specification. This is very important. Now, you can this data, the depth of discharge versus cycle of failure, means your batteries have a limitation. You have to replace the battery depending on the state of charge at which you are operating. For a particular day, what is the minimum state of charge? For next day, what is the minimum state of charge? So you have to take the average of all the minimum state of charge. Okay. So you have to think about, this is the data which is provided by the manufacturer data. Cycle of failures and in the x-axis it is written as average depth of discharge. So if the average depth of discharge is 80%, you can directly see that number of cycles have been reduced to 1000. You can see that it is 80. So number of cycles is 1000 only. If you are means 20% state of charge is there, so number of cycles will be 1000. Now if it is 30% state of charge, its number of cycles is increasing in this way. So you have to think about what should be the minimum state of charge. If you go further below, the number of operating hours, number of cycles will be reduced. You have to replace the battery continuously. That is very important. So accordingly, you have to finalize this important point where you have to operate. Okay. We have considered it to be 20%. Okay. Similarly, what should be the total cycles of failure? You can directly find out. Now, 3 different specifications of batteries were considered for optimization. Okay. Now, similarly, for charge controller cost, the charge controller is carrying the amount of amperes. It is carrying the amount of amperes. So we have to think about what are the total number of charge controllers which are connected in parallel. So what will be relative cost? You can directly figure out from these characteristics. Ampere versus cost of the charge controller. Now finally we can reach into the cost of energy. So in the cost of energy is considered to be the objective function in my problem. There TNPC is given into CRF. What is TNPC? It is the total net present cost of the system. Net present cost is given as the investment cost of all the components plus maintenance and operation cost in a particular year of all the components, multiplied with CRF, that is capital recovery factor. It is the capital recovery factor which depends on the discount rate and the escalation. Means whatever products you are purchasing, the material cost can change. That is the escalation cost of the material, and the discount rate is given. So in terms of these 2 important factors, the CRF is dependent on these important factors. So TNPC into CRF is the total annualized cost. That is given TAC, total annualized cost, divided by EGen. EGen is the total electrical generation that you are providing in a yearly basis. EGen is given as T equal to 1 to 8760, total number of hours. What is the total generation? And in the numerator, it is total annualized cost. Now, as we have discussed, what is the variation? SPV, number of diesel generator, number of batteries. We are varying these important sizes of these important components whose minimum upper and lower bounds are given. You can consider. Now, what are the constraints? Energy balance we have discussed. Total demand must be, your generation needs to be greater than the demand. Energy index ratio, ENS is the total number of hours for which load is not supplied. Expected energy not supplied. ENS means expected energy not supplied. So expected energy not supplied means what are the total number of hours for which load is not being met by the generating system. Divided by E naught. E naught is the overall demand in yearly basis. So whenever ENS will be 0, that is always you are providing the electricity. That means EIR will be 1 always. So this is important constraint. We have optimized the system where EIR should be 1. That is ENS EENS should be 0. Okay. So renewable, another important factor is renewable factor. If the government has some norms that 20%, 30% you have to use renewable energy. So you can also apply constant renewable energy factor constant, that is 1 minus summation of overall power given by the diesel generator divided by total generation into 100. Now CO2 emission. I was discussing about the initially environmental factor that I have considered, renewable factor and energy index ratio. Energy index ratio is technical parameter. Energy balance is also a technical parameter, and the optimization function is economic parameter. Okay, so you have to think about all the parameters. Socio-political I have not covered up, but you can also consider socio-political, which is basically the awareness or in job creation. Last important factor is CO2 emission. GNNET is the total gas which is emitted by the diesel generator when it is operated within a year. Okay, it is converted into kgs. ET, it is converted into tons, you can say kg or in tons. We are converting with the help of this quantity. En is the total number of total kilowatt hour. Energy is in terms of kilowatt hour. Total amount of kilowatt hour wherever diesel generator is operating into GNNP. The value is given 0.772 kg per kilowatt hour. When we multiply that, it is converted into kg. So we can find out the overall tons or kg of CO2 emission. Finally, I am not going into the details of the simulation that I have used, VBO algorithm. Here, basically, we have used this VBO algorithm for performing the optimization. You can go through it, no problem, no issues, whenever time will be there, okay? But important factor is that if we talk about the overall simulation, main thing is there are resource assessment. Different resources are given that we have discussed. These are the resources. Now, initialization, D is the total number of days and H is the total number of hours. So you can directly think that upper loop is our total number of days, 365 days. So your for loop is moving 1:365. Here total number of hours is 1:24. 24 into 365 into 24, it is operating for 8760 hours. Now there is a dispatch strategy that I was discussing. In the dispatch strategy, the cycle charging dispatch strategy, it is very important. There it is giving us the minimum results, better results. What is cycle charging strategy? Actually, there is a demand, there is a priority. We are considering the renewable generators to supply the demand first. That is given the priority. If renewable generators are unable to supply the demand, we are using the batteries to supply the net demand. If the battery SOC reach 20%, state of charge 20%, we have to cut it out. We have to remove the battery and we have to operate the diesel generator to supply the net demand as well as to charge the remaining portion to the batteries. Is clear? This is the cycle charging strategy. Now, what are the results that we can obtain? We just think about it. There were two different types of solar modules that we have considered. Two different types of batteries we have considered. And three different types of diesel generators we have considered. So 2 into 2 into 3 will be 18 combinations. So here you will find that 18 combinations will be there. 1, 2, 3, 4, 5, 6, 7, like that. 18 combinations will be there. So for 18 combinations of these SPD, battery and diesel generator, we can obtain 18 different results. 18 different results. And the simulation is optimized using VBO, GA and PS algorithms. Now for the third, 9th and 15th combinations, we are getting the minimum cost. And for 15th combination of load following is another dispatch strategy and cycle charging. Basically in load following, the difference is that we are not charging the batteries with diesel generator. We are only supplying the net demand. That is the difference. Now here for the 15th combination, the cost is, you can say, 5.76 rupees per kilowatt hour. And for cycle charging, it will be 5.46 like that. Okay. Renewable factor is better in case of load following. Why it is better? Because we are not using the diesel generator to charge the batteries. So diesel capacity has been reduced. Because we have reduced the diesel capacity, that means the renewable factor will be increased and the CO2 emission also be reduced because diesel generator is less used compared to the cycle charging strategy, where it is also using to charge the battery diesel generator. Now these are the two important cases because in load following the CO2 emission and the renewable factor is better, and in terms of cost if we think cycle charging is better. So if we consider these two important factors, important cases, now this will be okay. We will go through the analysis considering these two important considerations. Now CCS, this is very important to understand. This is a summer day. The there is a area curve. The brown color curve, light brown color curve is the area curve, which is showing the demand. Okay, which is showing the demand. The red bars, small bars, are the renewable generating system. These red bars are the renewable generating systems. Okay, the green bar, the green are the SPV power from SPV. Okay, you can see that load is given in this color, renewable generation in red color, solar is in green, discharge is in violet, and diesel is in blue, light blue. Now, how cycle charging is being operated here, it will be interesting to understand. Here, the area curve is given, which is the load curve. Now, when in CCS, what is happening? When the load is, when the renewable generator is given the priority. So, initially the red bars are sufficient to supply the demand. No other generators are there. But whenever demand is increasing, then we are going for the violet color bar, that is the discharge from the batteries. Okay, and similarly the second curve you can see that the initially, because the generation is more than the demand, the net demand is being supplied by the renewable generators to charge the batteries. So state of charge of the batteries are increasing. And in the fifth hour, when the discharge is there of the batteries, our state of charge is reducing. This is state of charge is reducing till the 7th hour. Since in the 7th hour, our SOC is near to the 20%. We cannot afford to operate the batteries here. So we are using the diesel generator, which is shown by the light blue color. You can see that light blue color is there in the 8th hour. So you can see this is the cycle charging strategy which is considered for summer day and for the winter day. Similarly for the winter day. Now, with the help of this, you can find out initially the sizing of the system was not written. The size of the systems components were not written. Now the size of the system components have been, you will optimize. After optimizing, these are the values that you can obtain. Now this is the second part is very interesting. It will be much more interesting. Now, as the villages are located in hilly area, so we have to electrify them. So to provide electricity, we have to construct the electricity distribution system, the transmission system. So for that, we have to extract the digital elevation map. This is the digital elevation map of the area. Okay, digital map, elevation map of the area. Elevation of each dot is given. We have extracted with the help of R3I software. Now you will find that a cross section is considered. Now what is the total number of villages? 7 villages were there. Okay. One is the hydropower. One is hydropower site. Another will be your generating center. I think you have gone through the load flow analysis. You have studied the load flow analysis. Load flow, Newton Raphson, Gauss-Seidel.
Yes.
Okay. Okay. So that will be interesting to incorporate here. We have estimated the size of the system. Size of the system has been finalized. But because these villages are not located in a plain land, so we have to think about the distance between the distribution system. In plain land, we can directly connect from A point to B point. But in hilly area, because of uneven locality, uneven altitude, we have to find the shortest path. आप सोचेंगे कि यहाँ से लेके आप नीचे दूसरी जगह पहुंच जाएंगे, आपको पूरा नीचे से जाना पड़ेगा. आप दूसरे पहाड़ से तीसरे पहाड़ से पहुंच जाएंगे. That will be of smaller distance. sometimes. So you have to find the shortest path. So to reduce the minimize the overall power loss cost, power loss को भी हमें कम करना है, and we have also to reduce the distribution system implementation cost. दोनों को reduce करना है. That's why we have considered this digital elevation map. In the digital elevation map, we have to place these villages and the hydro center. अब ये interesting point है जो मैंने research जो that I was involved here. Okay. So in this area, we have considered a section. ये सोचिए एक village है, ये दूसरा village है. ये one, this is one village, this is second village. Before going into this, there is another important point that I have to consider here. There are 7 villages. Okay, so 7 villages have a peak demand. I am also only considering the peak demand. We are designing the system according to the peak demand. So there will be a real power and there will be a reactive power. So real power and reactive power of at the peak time of each village will be summed up. Okay. Why this? I'm summing the real powers and reactive powers because we have to find out the generating center. There is a formula that is Berry center formula. With the help of Berry center formula, we can obtain the generating center where all the generating systems can be placed. That is diesel generator, SPV, and the power electronics. All these systems can be placed in a particular place. That can be calculated with the help of Berry center formula, which is calculated by summation of all the powers of each villages of real power and reactive power. There is a formula with the help of which you can find the generating center. So there are 9 points, 7 villages. One is the hydro center, another is the generating center from the Berry center. Now, interesting point is to consider is that we can consider two points at a time. We can consider 2 villages load centers or a load center and generating center like that. We have considered 2 centers. One is the source, another is the destination. So we have to connect the source point to the destination point with the help of distribution system. ये देखिए, this is a section. Okay. अब इसको then we have moved from this 3D model to 2D model. 2D model में हम लोग गए. In this case, we have to think about what are the total number of. देखिए, एक है latitude, एक है longitude. You can see this is latitude, another is longitude. The third dimension is elevation. So if we consider the 2D model where latitude and longitude is there, we can think of total number of longitude ज्यादा है कि total number of latitude ज्यादा है. यहाँ पर देखिए total number of longitude ज्यादा है यहाँ पर. So since the total number of longitudes are more, so we have to consider the total number of nodes will be equal to total number of longitudes. That is the idea that I have given. Okay. So number of longitudes will be equal to total number of nodes. Now this movement of these nodes will depends on the latitudes. So what are the total number of longitudes? Let us consider 10 longitudes are there. So for 10 longitudes, there will be 10 nodes and the movement of these nodes will be on the latitudes. So there are 4 possibilities. 4 latitudes are there. That means first node can be moved to 4 locations. Like that. इसके थ्रू हमने ऑप्टिमाइज करना है इनके नोड्स को. If we are able to optimize the nodes, we can reduce the overall distance from the generating center to the destination center. Generation ये जो source point है और destination point है, इन दोनों को हम लोग जोड़ सकते हैं इनको ऊपर नीचे करके. इनको कैसे कैलकुलेट करते हैं? ये फॉर्मूला बेसिकली ये फॉर्मूला दिस इज कॉमन फॉर्मूला दैट इज x1 minus x2 होल स्क्वायर प्लस y1 minus y2 होल स्क्वायर होल रूट. ये हम लोग यूज करते हैं नॉर्मल 2D के केस में. लेकिन 3D के केस में क्योंकि एलिवेशन है, सो वी आर कंसिडरिंग, जैसे सोचिए ये n1 नोड है, ये nj नोड है, इन दोनों का जो एलिवेशन डिफरेंस है दैट इज गिवन बाय द डेल्टा. ठीक है. सो यहाँ से जो आपका डिस्टेंस आया दोनों x1 minus x2 का होल स्क्वायर प्लस y1 minus y2 का होल स्क्वायर होल रूट, ये जो डिस्टेंस आया इस डिस्टेंस का स्क्वायर प्लस डेल्टा ni nj का स्क्वायर, जो कि एलिवेशन डिफरेंस है. इन दोनों नोड्स के बीच में एलिवेशन डिफरेंस है. दोनों का समेशन करेंगे, दैट वी विल गेट दी ओवरऑल डिस्टेंस, एक्चुअल डिस्टेंस। ये डिस्टेंस नहीं, हमें ये डिस्टेंस मेजर करना है एक्चुअली। दिस इज नोन एज यूक्लिडियन डिस्टेंस, इज नोन एज यूक्लिडियन डिस्टेंस। अब इन दोनों नोड्स के बीच में आपने फाइनलाइज किया, ऐसे सारे नोड्स को आपने फाइनलाइज करना है और सबका समेशन आपको देगा ये टीडी वैल्यू। तो यू कैन ऑप्टिमाइज दिस मूवमेंट ऑफ दीज नोड्स, यू कैन फाइंड द ओवरऑल डिस्टेंस। इस तरीके से आपका पाथ बन जाएगा, देखिए इसलिए पाथ, इस तरीके से पाथ आपका बन जाएगा यूजिंग सम ऑप्टिमाइजेशन टेक्निक दैट आई हैव कंसीडर्ड बीबीओ टू दिस केस। इसके थ्रू आप ऐसे लाइन बना सकते हैं। थोड़ा बढ़ा दीजिए, जस्ट कंटिन्यू इट। कंटिन्यू बटन, कंटिन्यू। तो देखिए ये इस तरीके से हमने एक सेक्शन का निकाला, ऐसे आप हर सेक्शन का निकाल सकते हैं। आप एक बार उसको चला दीजिए, हैंग हो गया है। एक बटन आप थोड़ा सा मूव कर दीजिए। ओके, आई थिंक इट इज करेक्ट। तो इस तरीके से आप पूरा देखिए, ये जो डीएम है, डीएम, ये पूरा आप रूट मैप बना सकते हैं इसका। तो डिस्ट्रीब्यूशन लाइन का आपका पूरा आपने रूट मैप बना दिया। अब ये जो रूट मैप है, ये बेसिकली क्या है, ये सारा ऑप्टिमाइज रिजल्ट है। दो दो लोकेशंस का हमने डिस्टेंस को ऑप्टिमाइज किया और सबका समेशन इनको जोड़ के वी आर गेटिंग अराउंड 16 किलोमीटर का हमें डिस्टेंस मिला इनको कनेक्ट करके। तो हमने सिंगल लाइन डायग्राम बनाया इसका, 9 बस सिस्टम का सिंगल लाइन डायग्राम बना के वी आर ऑब्टेनिंग द वोल्टेज ड्रॉप, है ना। एनआर मेथड यूज करके हमने पर यूनिट वोल्टेज ड्रॉप देखा हर बस में। सो वी आर फाइंडिंग these are the conductors that I had chosen, ACSR conductors। the Wiesel Farad ये सारे कंडक्टर्स हैं, इनके कॉस्ट दिया हुआ है रुपीज पर किलोमीटर, है ना। इनके पावर लॉस जो कि आपने कैलकुलेशन से निकाला है इंटरनैप्शन मेथड से, देन फाइनली ओवरऑल कॉस्ट आपका यहाँ पर दिख रहा है। एक इंपॉर्टेंट थिंग है, देयर इज एन इंपॉर्टेंट थिंग इज दैट द पीक डिमांड, व्हाट इज द पीक डिमांड, अराउंड 102 किलोवाट वाज देयर पीक डिमांड। द पावर लॉस हियर फॉर दिस कंडक्टर इज 5 किलोवाट। तो दिख रहा है लिंक में आपको 5 किलोवाट दिख रहा है लोड। सो 5 किलोवाट इज विद इन द रेंज ऑफ 5% लॉस। 5 किलोवाट इज विद इन द रेंज ऑफ 5% लॉस। सो दैट, सो यहाँ तक हम कंसिडर कर सकते हैं मिंक को। मिंक के नीचे, मिंक के ऊपर जाएंगे लॉसेस के टर्म में, वेजल फेरेट, इनके कॉस्ट तो कम है लेकिन यहाँ पर लॉसेस बहुत ज्यादा है। सो मिंक के नीचे अगर जाएंगे तो कॉस्ट हमारा बढ़ जाएगा। देखिए तो हमारा जो कंडक्टर का डायमीटर है वो बढ़ रहा है, नीचे जाएंगे। वेजल से लिपर्ड की तरफ जाएंगे तो हमारा कंडक्टर का क्रॉस सेक्शनल एरिया बढ़ जाएगा। क्रॉस सेक्शनल एरिया बढ़ जाएगा तो पावर लॉस आपका रिड्यूस होता रहेगा। That's why we have considered the mean conductor, and the mean conductor also you will find that the per unit drop is 0.9। ये 0.9 है ना। बस का जो पर यूनिट वोल्टेज है जो 6, 8 और 9 बस में ये 0.9 से ऊपर है इन केस ऑफ मीन कंडक्टर। ये दोनों रीजंस मिला के वी आर सिलेक्टिंग द मीन कंडक्टर। फाइनल इंपॉर्टेंट पार्ट जो हमने इमिशंस को देख के बताया कि इमिशंस को कैसे कॉस्ट के टर्म में कन्वर्ट करते हैं। सो एक डॉक्यूमेंट है, देयर इज अ वन डॉक्यूमेंट इन यूनाइटेड नेशंस का एक डॉक्यूमेंट है और वहां पर डॉक्यूमेंट है कि $10 या 100 या $11 पर टन ऑफ CO2 एमिशन पे चार्ज किया जाता है। मतलब एक टन ऑफ CO2 अगर आपने इमिट किया, $11 का पेनल्टी लगता है, $10 to $11 का पेनल्टी लगता है। सो यहाँ पर देखिए CS इज द कॉस्ट सेविंग। CS is the cost saving for not emitting CO2। WET क्या है? WET वो कंडीशन है जब खाली डीजल जनरेटर से अगर मीट करेंगे हमारे ये डिमांड को, तो वो जो एमिशन होगा वो WET। WET is the total emission when we use CCS, LFS जो भी डिस्पेच स्ट्रेटेजी था उसको यूज करेंगे। सो व्हाट इज द अमाउंट ऑफ CO2 emitted there। तो इन दोनों का जो डिफरेंस है वही हम सेव कर रहे हैं कॉस्ट के टर्म में, इनटू N। N is the total number of years of operation into 60। उस टाइम पे $60 पर डॉलर पे 60 रुपीज था, तो मैंने 60 उसको काउंट किया था इंटू 10 $10 पर टन, 1000 से डिवाइड किया ताकि टन में कन्वर्ट हो जाए केजी को। तो दिस इज द एक्चुअली कॉस्ट के टर्म में हमने CO2 एमिशन को कन्वर्ट कर दिया। नाउ ओवरऑल COE जो कॉस्ट आया वो किस उसमें क्या क्या आया, कंडक्टर का कॉस्ट, ये जो कॉस्ट आया आपका 1 करोड़ रुपए आया मिंग कंडक्टर में। देन TNPC, ये जो कंडक्टर का कॉस्ट आ रहा है इसमें सारा कॉस्ट इन्वॉल्व है ना, इसमें आपके ट्रांसफॉर्मर्स और ये 3 फेज 4 वायर सिस्टम है, ये पूरा कॉस्ट आपका इंक्लूडेड है, ये गवर्नमेंट का ही डेटा है एक्चुअली, वहीं से लिया गया। तो CCT इज द ओवरऑल कॉस्ट, यहाँ से आया 1 करोड़ रुपए। TNPC इज द कॉस्ट ऑफ, जो हमारा CRF छोड़ के जो कॉस्ट आया था, मतलब इन्वेस्टमेंट कॉस्ट ऑफ द इक्विपमेंट्स और एज वेल एज द मेंटेनेंस कॉस्ट, वो आपको TNPC आया, माइनस ये जो एनर्जी सेविंग हो रहा है कॉस्ट के टर्म में आपने जो सेव किया, माइनस करके CRF से मल्टीप्लाई करके यू आर डिवाइडिंग द रीजनरेशन, वी आर गेटिंग द ओवरऑल COE। ठीक, अब यहाँ से आप कंपेयर करेंगे विदाउट ये दोनों पैरामीटर्स लेके COE CO2 एमिशन एंड विदाउट कंडक्टर कॉस्ट, तो आपका कॉस्ट अलग अलग आएगा। अब सब मिला के अगर कंडक्टर का कॉस्ट भी देखें, CO2 एमिशन भी देखें और इनिशियल COE कॉस्ट भी देखें, उस कंडीशन में साइकिल चार्जिंग आपको मिनिमम कॉस्ट दिखाएगा। That's why we are considering this system। और यहाँ से हम कंक्लूड ये कर सकते हैं कि we are able to estimate the resources very accurately, near to accurately, then sizing of the system components is possible and selection of the conductors for distribution system। now यहाँ पर रिसर्च का कहाँ एरिया है जो मैं आपको बता रहा हूँ, according to my experience I can say first important thing is that ये वाला जो पोर्शन है जहां पर शॉर्टेस्ट पाथ आपको निकालना है फॉर फाइंडिंग आउट फॉर डिस्ट्रीब्यूशन सिस्टम, सो ये चीज नया है, इट वाज नॉट देयर एनीवेयर। सो इस पे आप काम कर सकते हैं। इस पे और एक चीज है कि फॉरेस्ट एरिया, आपके पास यहाँ पर मैंने फॉरेस्ट एरिया कंसिडर नहीं किया है, अगर आपने यहाँ पर फॉरेस्ट एरिया कंसिडर किया होता तो इसका डिस्टेंस डायग्राम अलग होता, ठीक है ना। तो एक प्रॉब्लम यहाँ पर है, दूसरा प्रॉब्लम ये है कि DSM आपके पास जो लोड्स हैं उसमें कुछ डिफरेबल लोड्स भी हैं और कुछ शिफ्टेबल लोड्स भी हैं। जैसे आपके पंप्स हैं, वाटर पंप्स तो आप किसी भी आवर पे ऑपरेट कर सकते हैं, तो वाटर पंप्स को उस आवर पे क्यों ऑपरेट करना है जहां पर पिक लोड है, हम दूसरे आवर्स पे ले जाए तो उसको हम फजी के हेल्प से हम शिफ्ट कर सकते हैं विद द हेल्प ऑफ फजी लॉजिक एंड डिफरेंट आर्टिफिशियल इंटेलिजेंस। पहले दिन का प्रीवियस डे का एनालिसिस आपके पास है, नेक्स्ट डे का क्या होना चाहिए आपको पता है, क्योंकि लोड में बहुत ज्यादा फ्लक्चुएशन नहीं आएगा, है ना। तो आप शिफ्ट कर सकते हैं कि आवर पे आपके पास जनरेशन ज्यादा है उस आवर पे शिफ्ट कर लेंगे आप, है ना। पंप को नहीं तो आप सोचे जो 100 मिल है, फ्लावर मिल है, उस घंटे के लिए हमने शिफ्ट कर दिया। सो ये भी इंपॉर्टेंट फैक्टर है। कंस्ट्रेंट सिलेक्शन, ये एक बहुत प्रायर चीज है कि कौन से कंस्ट्रेंट सिलेक्ट करेंगे एक पर्टिकुलर डिजाइन के लिए। आप जो मॉडल डिजाइन कर रहे हैं, जो आपने हाइब्रिड एनर्जी सिस्टम, रिन्यूएबल एनर्जी सिस्टम डिजाइन कर रहे हैं, कौन से एरिया के लिए कर रहे हैं, उनका कंस्ट्रेंट क्या है। तो कंस्ट्रेंट सिलेक्शन इज वेरी इंपॉर्टेंट पार्ट ऑफ ओवरऑल डिजाइनिंग द प्रॉब्लम। फिर इंस्टॉलेशन, पूरा ओवरऑल डिस्ट्रीब्यूशन सिस्टम का, पावर सिस्टम का पूरा कॉस्ट का एनालिसिस आपको करना है। फिर कंट्रोल सिस्टम का एनालिसिस करना है। यहाँ पर कंट्रोल का उतना नहीं इसलिए आ रहा है क्योंकि ग्रिड कनेक्टेड सिस्टम नहीं है। ग्रिड कनेक्टेड सिस्टम होता तो आपको कंट्रोल के बारे में भी सोचना पड़ता। Okay, these are very important factors that I have to